let's talk about electrostatics. And we're done already with the charges. We have the positive charge and the negative charge. Once we say positive charge, an object loses electrons, and once negative charge, an object accepts electrons. We have the principles of electrostatics, wherein we have ways on how to charge an object. We have charging by induction and charging by conduction. Next, we're already done with the discussion of electric fields. This is the picture of an electric field from positive to negative charge, positive to positive charge, negative to negative charge. I also uploaded videos about applications of electrostatics, such as the lightning, anti-static bag, photocopiers, electrostatic precipitators, spray painting, and Van de Graaff generator. Now, this day, we're going to focus on problems and formulas. We have these three special problems that talks about electrostatics. We have problem number 1, electrons charge. We also have the force constant as well as the electric field. Let's start. For problem number 1, we have here charge to electrons. What is the charge of 1.25 times 10 raised to 30 electrons in coulombs? First, we'll write the given and the required. So we have here the given 1.25 times 10 raised to 30 as the number of electrons, and we're looking for the charge in coulombs. For our equation, we have to take note that for every 1 coulomb, there is 6.25 times 10 raised to 18 electrons. So we're gonna multiply this by our dimension, and we're putting this 6.25 at the denominator side for us to cancel the unit, so we could cancel now the electrons, and then we have 1 coulomb on the numerator part. By pressing the calculator, the answer here for 1.25 times 10 raised to 30 divided by 6.25 times 10 raised to 18, here we could have 2.00 times 10 raised to 11 coulomb. So this is the final answer, 2.00 times 10 raised to 11 coulomb. Now, what if you don't have a calculator? We can see that 625 is a multiple of 1.25 or 1250. So we could adjust this by 625 times 10 raised to, so 1, 2, and then this would become 16. And then this 1250, so we'll make this as 1250, 1, 2, 3. And then this would become times 10 raised to 27. So from 30, then 29, 28, 27. And then 1250 divided by 625 is 2 times 10. And from here, 27, 10 raised to 27 divided by 10 raised to 16 is 11. So the final answer, we got the same answer, 2 times 10 raised to 11 coulombs. Next, problem number 2, how many electrons are there in 5 microcoulombs? We could start first writing our given. The given is 5 microcoulomb, and the required is the number of electrons. We have to take note that for every 1 microcoulomb, that is 10 raised to negative 6 coulomb. And we should always recall that for every 1 coulomb, that is 6.25 times 10 raised to 18 electrons. First, we're going to write 5 microcoulomb multiplied to, so we have here 1 microcoulomb, and is 10 raised to negative 6 coulomb. Then since we're looking for the number of electrons, this 1 coulomb, I will write here at my denominator part so that I can cancel it. And then this 6.25 times 10 raised to negative 18, I will write it on the numerator part. And as you can see, I can cancel now my units. So microcoulomb, cancel the microcoulomb, coulombs could be cancelled by the coulombs. And solving now, we have here 5 times 10 raised to negative 6 times 6.25 times 10 raised to 18, and then we have here the electrons as our unit. Now, we have to take note that the 6.25 times 10 raised to 18 can be written as 625 times 10 raised to 16 times, we have here 10 raised to negative 6, and take note we have here the number 5, and the 625 can be expressed as 25 square. And furthermore, this 25 is equivalent to 5 square. So we have here this 5 square and square it, that is simply 5 raised to 4. So if I'm going now to write my final answer, which is 5 multiplied to 5 raised to 4 times 10, we have here negative 6 times 10 raised to 16. So we have negative 6 plus 16, we have here 10. And our final answer would become 5 raised to 5 times 10 raised to 10. And what is 5 raised to 5? That is 625 multiplied to 5. That is actually equivalent to 3,125 times 10 raised to 10. Adjusting this, so from here 10, that would become 1, 2, 3. So we have 10, 11, 12, and 13. And then therefore, our final answer can be written as 3.125 times 10 raised to 13 electrons. Now, how about the second question? How about 1,000 millicoulombs? So again, our given, we have here the 1,000 millicoulombs. And the required, again, is the electrons. Let me erase first this problem number 1 or question 1. Now, for our equation, we have to take note that for every 1 millicoulomb, that is 10 raised to negative 3 coulomb. And remember, for every 1 charge of coulomb, we have 6.25 times 10 raised to 18 electrons. So let's do now our solution. We have 1,000 millicoulomb times, for every 1 millicoulomb, we have here 10 raised to negative 3 coulomb times, for every 1 coulomb, we have 6.25 times 10 raised to 18 electrons. And then therefore, we could now cancel the units. We have microcoulomb cancelled, we could cancel down a millicoulomb, and then we could cancel also the coulomb. And then remember that this 1,000 can be written as 10 raised to 3. And then solving now, we have 10 raised to 3 times 10 raised to negative 3 times 6.25 times 10 raised to 18 electrons. So 10 raised to 3 times 10 raised to negative 3, that's 10 raised to 0, that's equivalent to 1. And then therefore we have here 6.25 times 10 raised to 18 electrons. So that's the final answer. Now let's talk about electric force, where we define it as a force of attraction caused by two charged bodies. And this electric force has been studied by Charles de Coulomb around 1730s. So we have 1736 to 1806. According to him, the electric force between the two charged bodies parallels Newton's law of gravitation. We have here the force is inversely proportional to the square of the distance or the radius and directly proportional to the charges. Remember that the Newton's law of gravitation is written as force equals to multiplied to G multiplied to mass 1 times mass 2 over the r square. For Coulomb's law, we have here force is equals to K multiplied to the Q1 times Q2, get their absolute value, divided by the square of the distance or the radius. Now, we have to take note the value of K, which is 8.99 times 10 raised to 9 Newton meter square over column square, or this can be rounded off as 9 times 10 raised to 9 Newton meter square over column square. Physicists found out that the value of K, they derive it from this relationship wherein 1 over 4 pi multiplied to epsilon. This epsilon is known as permittivity or electrical permittivity. This electrical permittivity is known as the extent which the medium permits an electric field to act between two charges. In a vacuum, this permittivity, the value of that is 8.85 times 10 raised to negative 12 column square over Newton multiplied to meter square. So plugging in this value of 8.85 times 10 raised to negative 12 with the value of epsilon here, we now have our constant, which is 9 times 10 raised to 9 Newton meter square over column square. And once we're using this value of K, we use this constant. We have to keep in mind that we are computing for the electric force. So in our problem, two equal charges are located 16 centimeters apart in a vacuum, and they repel each other with a force of 0.28 Newton. Find the magnitude of each charge in coulombs. So we have to write now our given and the required for the problem. So we write now the given. So we have here the radius is 16 centimeter. Now don't forget that we need to make it into meter. That's 0.16 meter. And for the force, we have here as a 0.28 Newton. And how I know that's a force, because of the unit, we have here 0.28 Newton. The required for a problem is the magnitude of each charge. Now let's go now to our equation. So that is simply force is equals to K multiplied to the first charge Q1 and then second charge Q2 divided by the R square. Since we're talking about the same charge, same body with the same charge, therefore we could have K multiplied to the absolute value of Q square over R square. Solving for the value of Q, we have here F multiplied to R square divided both sides by K, and then we have here the Q square. Solving for the Q square, we have the square root of F multiplied to R square over K, and then therefore the value now for RQ, for the charge, that is simply R multiplied to the F over K. Plugging everything, we have here Q is equals to the positive and negative. Since we're getting the square root, the value of R here is 0.16 meter multiplied to the value of force, which is 0.28 Newton, divided by the value of K, which is around 9 times 10 raised to 9 Newton meter square over column square. And let's see how the units are being cancelled. Newton here is cancelled. Meter square, you get the square root and then you cancel it here with the meter. And then we have now the column square, and then you square root it. Our unit would be coulomb. So if you press it in the calculator, the value here is somehow 8.9 times 10 raised to negative 7 coulombs. And that is positive, negative. Now, since we're talking about the magnitude of each charge, we don't know, but you could say it is positive coulomb or negative coulomb, and It doesn't say in the problem. And therefore, we could also state that this charge is equals to positive or negative 0.89 microcoulomb. However, this answer will be accepted and correct. Next, problem number 2. A positive charge of 5.2 times 10 raised to negative 8 coulomb is located 5.45 centimeter from a negative charge of 1.7 times 10 raised to negative 7 coulomb. Calculate the force exerted by either charge upon the other. So let's try to write first the given. So here's the given. We have the first charge body, 5.2 times 10 raised to negative 8. The second charge body, we have 1.7 times 10 raised to negative 7 coulomb. And the value of K, we have 9 times 10 raised to 9 Newton meter square per coulomb square. And this 5.45 centimeter, we have to take note that we have to convert it to meter. So divided by 100, and that is 0.0545 meter. In order for us to compute for the force, we have this equation. Force equals to K multiplied to Q1, absolute value multiplied to Q2, then get the absolute value, then R square. The solution is easy since this will just require a direct substitution, wherein the value of K is 9 times 10 raised to 9 Newton meter square over the coulomb square, multiplied to the charge, which is 5.2 times 10 raised to negative 8 coulombs, and then the other charge is 1.7 times 10 raised to negative 7 coulomb, divided by the radius 0.0545 meter, and then we have to square it. Pressing it in the calculator, the value will be force equals to 0.02678. Now we have to take note what's the unit since we're looking for force, therefore the unit is Newton. But we have to show the cancellation wherein coulomb times coulomb, that is coulomb square, this will be cancelled. Meter, you square it, that will become meter square, that will be cancelled. Therefore, we only have Newton as our final unit. And then rounding off to two significant figures, since on the problem we have here the two significant figures, so our final answer must be in two significant figure, and then therefore it is 0.027 Newton. Take note that this force is very weak, and that is 0.027 Newton as compared with the other forces of attraction. Let's go now with the definition of electric field, wherein once we say electric field, it is the region in which an electric charge experiences an electric force. The symbol for electric field intensity is letter E, which means electric field strength. Therefore, we defined it as the force act on a specific charge at some distance. So here's the equation. The electric field strength is F over Q sub O. This Q sub O is known as the test charge. An electric field is a vector quantity wherein we could represent it by positive and negative charge. Once we have a positive charge, the arrow points outward, and we represent the negative charge, the arrow is pointing towards the charge. This is the representation of how the electric fields for two unlike charged bodies. This is for the like body. We have the negative and the positive. Take note of the electric field, that the direction of the electric field, and it explains why there's no attraction or there is an attraction of the two charged bodies. Since the electric field strength is F over the charge point, and we could represent the force as K multiplied to Q1 times Q2 over R square, then divided by QO. This one represents as the force. And we could take note that we could have another equation wherein electric field strength, that is, we're gonna cancel this QO and the QO, and then we have now K multiplied to Q2 over R square. So this is another equation for electric field strength. These two equations talks about electric field strength, but they are somehow different. This first equation, it talks about an electric field strength as the force of an electric field exerts on the charged body per unit charge. While this equation, it talks about the charged body's electric field strength at a position some distance from a charged body. So for this equation, if we have here the charged body, and then we're talking about the electric field strength at this or at some point of this area. So what could be the electric field strength on this part? How about on this part or on this part? So that's how the equation 1 goes. And for the equation number 2, if we have here the two charged bodies, and then we have here the two electric fields, okay? And then therefore, if we have here the two electric fields, example, if we have here the Q1 and then we have here the Q2, we're talking about the electric field experienced by this charged body with respect to this another charged body. So what is the electric field strength somewhere here or somewhere here or somewhere here with respect to this distance? An electron's charge is negative 1.602 times 10 raised to negative 19 coulomb. Calculate the force of an electron in an electric field 3 times 10 raised to 3 Newton per coulomb. Let's now identify the given and the required. So this is the given. We have negative 1.602 times 10 raised to negative 19 coulomb for the Q1. And for the 3 times 10 raised to 3 Newton per coulomb, that is the electric field strength. And the required here is the electric force. Since we define the electric force, wherein the electric field is equals to F over QO, and then therefore we could find the equation for the electric force, which is F is equals to electric field multiplied to the charge or the Q sub O. Now for our solution, that is simply a direct substitution. We have here the value of electric field strength, that is 3 times 10 raised to 3 Newton per coulomb multiplied to the charge, which is negative 1.602 times 10 raised to negative 19 coulomb. Then we could simply cancel the units, and then by pressing our calculator, the answer will be that force is negative 4.81 times 10 raised to negative 19 Newton. We have to take note that if we're going to imagine the strength of this force, this is a very, very weak force. And the negative here, it implies that the electric field and the force act in opposite direction. So here we have the next sample problem. A small steel ball hangs from a silk thread and is given by a negative charge of 2.6 times 10 raised to negative 7 coulomb. What is the electric field strength at a distance of 1 centimeter? Now we have to take note of the given as well as the required. So we have here the sample problem. The given is 2.6 times 10 raised to negative 7 coulomb, that is the charge. And we have also the distance, which is 1 centimeter or 0.01 meter, or represented as R. And we're looking for electric field. Now for the equation, we could write a 2, which is it could be E equals to F over Q sub O, or we have another equation which is E is equals to K multiplied to the absolute value of that charge divided by the distance square. Now, by looking at the given as well as the required, we have to take note that we don't need this equation. And we will be applying our equation 2. Now, for our solution, we have here E equals the value of K, which is for the K, that is 9 times 10 raised to 9 Newton times meter square over column square. For the value of the charge, we have here 2.6 times 10 raised to negative 7 coulomb. And for the value of the radius or the distance, we have here 0.01 meter, and then we have to square it. Pressing now the calculator, our answer for electric field is, so the answer here is 2.34 times 10 raised to 7. Now, what is the unit here? Let's take a look how we cancel the unit. Meter square will be cancelled with the meter square. And then we also have the coulomb. And then this one is the column square. So this will become the coulomb. And then therefore, the unit that we're going to have for electric field strength, we have Newton per coulomb. So this is our final answer. And that's it. That's all for electrostatics.